Okay, in our problem, we are going to find the maximum volume of a cone inside of a sphere. The problem reads, find the radius and height of a right circular cone of maximum volume that can fit inside a sphere with a radius of r. So we have our diagram. This is looking at the sphere. This is looking at the sphere from the side, where we have the base of the cone and the points or the sides of the base touching the sphere, and the top of the cone touching the sphere as well. So it's got its maximum height in there. Now the radius, the base of the cone, can change size as it changes inside the sphere, which will change its volume. So the radius and the height of the cone will change. So we're trying to maximize those dimensions to find the maximum volume that we can obtain. So we see that the radius is going to be of the cone is going to be represented by x, and to get the height, what we need to do is take it'll basically be the radius of the sphere plus this remaining part of the height of the cone. Now we find that by we have this right triangle that consists of the hypotenuse is actually the radius of the sphere, along with the radius of the cone being the other side. So we're able to find that remaining length of the height of the cone, just like that. So now we know that the volume of a cone is represented by 1/3 pi, and the radius of the cone, which is going to be x squared, times the height of the cone. So now we'll go ahead with that all set up. We're ready to take the derivative and proceed to find our optimum value for x.
Okay, so in order to find the maximum volume of the cone inside the sphere, we're gonna have to take the derivative. This is the equation for the volume, and to take the derivative, we're just gonna remember the derivative of a product is u primes times v plus u times v prime. So it's 1/3 pi times 2x times this whole equation plus the u, which is 1/3 pi x squared times 1/2 r squared minus x squared minus 1/2. Your r is a constant, so it's going to be 0 times the inside of the square root, which is minus 2x. And to simplify it, this is going to cancel out, so you're left with minus. It's going to be minus 1/3 pi 1/2. And can you stop? I forgot to add the x here, so this is supposed to be x cubed. So okay, Taylor gonna go ahead and solve for this equation, set it equal to 0.
So here's the derivative of the volume of the cone, all nice and solved out, and set equal to 0. So first we're going to divide by pi over x, and then we're going to add this to the other side of the equation. So after that, we get after that, we're going to multiply both sides of the equation by the denominator here. So that will get us Sorry about that, guys. I ran out of room there. So basically now what I'm going to do is I'm going to distribute the 2 here, and then after the 2 is distributed, I'm going to subtract 2r squared to this side, and then I'm going to add 2x squared to that side, and then I'm going to square both sides of the equation, and I'll show you guys what that looks like now. Okay, now like I told you, I'm going to square it. I'm going to give you guys a second look at that. And now I'm going to simplify it. Now what I'm going to do is I'm going to factor out x squared. Now notice we're trying to optimize the radius of this cone, so a radius of 0 wouldn't do us much good, so the radius cannot equal 0 in this case. So now I'm going to set it back equal to 0 and solve it. Okay, sorry guys, ran out of room again. Okay, now I'm going to solve for the radius. So we square root both sides of the equation, which gets us x equals 2 root 2r over 3. And notice that the radius can't be negative, so we're only going to take the plus version of this. So that's the radius. And now this is the equation that we had before for height. So now, I'm just going to, we already have x squared, so I'm just going to plug that in to the equation. So height equals the square root of r squared over minus 8r squared. Now I'm going to find a common denominator between both of them, which is going to be 9. And then after that, we get r squared over 9 plus r. And then finally we get 4r over 3 for the height. And that's the cone's radius and height maximized.